Good evening, everyone. I am Dhananjayan, Assistant Professor, Department of ECE, SRML Lima Engineering College. Now we discuss about the topic differential pulse code modulation. So differential pulse code modulation is shortly called as DPCM. Okay. So the use of PCM for the digitization of voice or video, the signal is sampled at the rate higher than the Nyquist rate. That is Fs greater than or equal to 2Fm. Okay, Fs greater than or equal to 2Fm. So at that rate the signal is sampled. Okay, so the resulting sampled signal found it exhibit the high correlation between the adjacent sample. So during the conversion of uh, during the conversion of analog to digital conversions, during the sampled high correlation is there. Okay, between the samples high correlation is there. Okay, so the meaning of high correlation is that the signal does not change rapidly from one sample to the another. That is, the difference between the sample has high variance. The difference between the sample has high variance. That is, the variance is smaller than the high variance. The difference between the sample has variance that is smaller than the variance of the signal itself. Okay, so the highly correlated samples encoded as in PCM. So the resulted signal contains redundant information. So the signal contains redundant information. So we removing the redundancy before encoding, we obtain the more efficient coded signal. That is nothing but differential pulse coded modulation. Differential pulse code modulations. So mainly we move on to the differential pulse code modulation to remove the redundant information before encoding. So this is the sample differential encoded modulation diagram. Okay, the analog signal is converted to the digital signals, okay, by the rate of Fs greater than or equal to 2Fm. In the DPCM modulations, redundant information, that is adjacent samples, okay, more number of adjacent samples, high correlated samples are reduced, okay, during the using the differential pulse code modulation technique. So in differential pulse code modulation technique, so the past signal up to this point is make some inference about its future values. Assume that the baseband signal x of t at the rate fs greater than fs equal to 1 by ts with the sequence produce the sequence with high correlated samples at ts seconds apart with the ts seconds. Okay, so baseband signal x of t is sampled at the rate fs equal to 1 by ts. That is the output of the baseband signal. Is sampled fs equal to 1 by ts to produce the sequence of correlated samples at ts seconds. Okay, let the sequence denoted as, that is the sampled sequence is denoted as x of nts. So x of t is nothing but baseband signal. The sampled signal is nothing but x of nts. Okay, x of nts. So it is possible to predict the future values of the signal x of t. So future x of t, the motivation is the differential quantization techniques. Differential quantization error. So this is the basic DPCM transmitter and a receiver block diagram. So in this transmitter in diagram, so the input signal, that is nothing but x of nts. So x of nts nothing but sampled input signal. So for the summer, one input is nothing but x of nts, that is sampled input signal. The another input is nothing but predicted sample x cap of nts, predicted sample signal. So both the signals are given to the summer. So here the output is nothing but e of nts. So the e of nts is nothing but prediction error signal. So E of NTS is nothing but difference of sampled input signal and predicted input signal. Okay, sampled input signal and predicted input signal. So E of NTS is nothing but prediction error. Okay, so the E of NTS equal to x of NTS minus x cap of NTS. Okay, then the E of NTS signal is given to the quantizer. It's quantized the E of error signal, quantized the signal its output is nothing but V of NTS. So the V of NTS is nothing but the quantizer output. It gives the output V of NTS. So V of NTS equal to Q of E of NTS, the quantized of E of NTS. So the Q of E of NTS is nothing but E of NTS plus Q of NTS. So error signal E of NTS plus Q of NTS, quantize the signal, quantize the error signal Q of NTS. So the Q of NTS is nothing but quantization error. Quantization error signal is nothing but Q of NTS. Okay. So after that, the V of NTS signal is given to that summer circuit, the summer block, and the summer in the summer block, one input is nothing but V of NTS, another input is nothing but predicted sample. So both the simple to this summer circuit, and the output of the summer is nothing but U of NTS. So the U of NTS is given to the predictor input. So U of NTS is predictor input, which is actually the summer output. U of NTS is nothing but summer output. Okay. Summer output of the predictor output and the quantizer output. Okay. So again it's produced the estimated signal. The same process is given again. So okay. So finally the V of NTS is given to the encoder. V of NTS is given to the encoder. Its output is nothing but V of NTS. V of NTS, after this encoder, it give the output V of NTS. This is nothing but DPCM waveform. DPCM. Okay. Differential pulse code modulation waveform. Okay. This is the transmitter side. In receiver side, you have the block consists of decoder and predictor. So the input is given to the predictor, and the feedback loop is here. The predictor, finally the predictor output is given to the summer, and the decoder output is given to the summer. Finally, it's produced the estimated signal output, estimated output in the output side. Okay. Then say equations: V of NTS equal to Q of NTS equal to E of NTS plus Q of NTS. Okay, E of NTS is nothing but the prediction error, Q of NTS is nothing but the quantization error. So prediction error plus quantization error is equal to Q of NTS. This is the Q of NTS is nothing but the quantized output. Okay, quantized output equal to E of NTS plus Q of NTS. Okay, so next one, E of NTS is nothing but X cap of NTS plus X cap of NTS plus V of NTS. So the V of NTS is nothing but E of NTS plus Q of NTS. Okay. So as per this block diagram, already we discussed. So X cap of NTS plus E of NTS is nothing but X of NTS. Okay. X cap of NTS plus E of NTS is nothing but X of NTS. Okay. So U of NTS equal to X of NTS plus Q of NTS. That is quantized version of the input signal X of NTS equal to X cap of NTS plus E of NTS, and the Q of NTS is nothing but quantization error. Okay. So finally we calculate the U of NTS. So the U of NTS is the quantized signal at the predictor input. It differs from the X of NTS, that is quantized version of the input signal by quantization error. It differs from the X of NTS and Q of NTS. If the prediction is good, the variance of the prediction error E of NTS will be smaller than the variance of X of NTS. Okay. If the prediction is good, prediction is perfect, the variance of the prediction error E of NTS will be smaller than the variance of the X of NTS. Next one, differential pulse code modulation, SNR value. So the output SNR is calculated by the equation SNR out equal to sigma square X by sigma square Q. So the X is nothing but the input, Q is nothing but the quantized signal. Okay. It is also rewritten as sigma square X by sigma square E into sigma square E by sigma square Q. Okay. Here for simplification we introduce the factor sigma square E, E for error, E for error. Okay. So here we note another parameter GP. So the GP is nothing but the prediction gain. Okay, we introduced the another factor GP. GP is nothing but prediction gain. Okay, so the prediction gain GP is nothing, GP equal to sigma square x by sigma square e. So this is nothing but prediction gain GP. Okay, so in this factor is introduced in this part, so this is replaced as GP, and sigma square e by sigma square q, it's written as SNRP. So P means prediction error, SNRP. So this is nothing but prediction gain, this is nothing but prediction error, SNR. Okay, so this is also, this is denoted as SNRP, SNR prediction error. Okay, prediction error to quantization noise error is nothing but sigma square E by sigma square E. The sigma square E is nothing but prediction error, sigma square Q is nothing but quantization noise ratio. That is, Q means quantization, E means error. Q means quantization, E means error. Okay, quantization error to prediction error to quantization noise ratio. Okay, here the factor GP, prediction gain, is greater than 1. If GP greater than 1, it's represent gain in SNR, that is due to the DPCM. It's represent gain in SNR due to the DPCM. For normally the baseband signal, the variance of the signal is fixed, so GP is maximum. Okay, if the variance is fixed, so the GP value is maximum. Okay, by minimizing the variance of the prediction error. So accordingly our main objective is nothing but design the predictor so as to minimize the error variance, mainly to minimize the error variance. Okay, this is our main objective, to calculate the SNR output. Okay, the main objective of the calculation of SNR output is minimize the error. Okay, thank you.